not going to see that. So that's a bummer, for them anyway, but that's on them for not showing up to lecture. Right, so last time we were talking about the potential energy function for gravity. I gave a very quick example. This is throwing a rock vertically and catching it. No, I don't have tea today. Unfortunately, Safeway was out of green tea. No, I know what I said wasn't in the recording. I'm aware of that. Anyway, I don't have green tea, Safeway is out, so I am just sad now. So another example that we can do regarding the potential energy function for gravity is a car going around a loop with no friction. T? I don't understand. Is T a cheating thing? I'm aware of Chegg and Course Hero. I know that they're, and Slater, I think. Oh, okay. Well, apparently I'm old. Anyway, it's okay, I forgive you. So let's say that we have our car, our terrible, terrible car, moving at some height. Maybe it's at some initial height, moving along some speed, moving in that direction, and then there's a loop-de-loop. Terrible loop-de-loop, I know. Car's, going along, doing its thing. And that will be at some other height on the loop-de-loop, it will be at some other speed, right? So one could ask, how fast is it going while it's at a certain height in the loop-de-loop? So we can use the energy conservation model and the potential energy function for gravity to understand this problem. So we know that there's no friction, and we're treating the Earth as part of our system, and we're treating the car as part of our system. So what do we have for our work-energy theorem? We have 0 on the left-hand side because there's no external work. And then we have the change in kinetic energy because the speed is changing, and the change in gravitational potential energy. And that's it. That's all that there is. And so the change in gravitational potential energy, well, that's just equal to mgyb minus mgya. It is just mg delta y, right? So we know what the we can also write out what the initial and final kinetic energies are, right? So this is 1/2 mvb, the speed at position b or at height b, minus 1/2 mva squared, and that's plus mgyb minus mgya. And so we have 0 is equal to this thing. Now we can do some algebra and we can solve for the speed vb at height yb. And after a whole bunch of algebra, all I'm doing is just rearranging this equation. You get square root of va squared minus 2g yb minus ya. Now, solving this problem with forces would have been a mess, like a huge mess, because there's normal forces that are changing directions, there's changing coordinate systems all over the place, but we can just easily find the speed at which it's going around the loop at a given height. And by the way, I'm sorry that you hate it. By the way that you can use this formula here is to think about what forces, or think about how the speed relates to the centripetal acceleration, and therefore what forces must be present. And I'm thinking about the homework here. If a car just barely makes it to the top of a loop, right? Speeding along just barely makes it to the top of the loop at some speed v, then we know that that there could have been 2 forces. There could be the normal force and the gravitational force. But if it just barely makes it to the top of the loop, that means that the normal force is 0. And so all that there is the gravitational force. And so the gravitational force, which is ma, has to be equal to mv squared over r. with the appropriate signs and everything. The whole point is that you can use this formula to find the speed and thus to find things like the radius or the gravitational force and so on. And that the reason I brought that up is because it's on the homework. So I'm going to pull something up really quick that you may have seen before. Not yub.com. Yeah, check is not free. The point is that there isn't normal force because it's just barely making it over the top. Come on. I would normally actually do this demo, but I realized that I probably can't because I don't have, you know, the demo at home. All right, we'll just have to skip this. I'll send an announcement with the demo I was talking about, what it is, later, and then you can watch it on your own time. Basically, it's just a guy who releases a pendulum with a bowling ball on the end right next to his face. It goes down, swings up, and it doesn't hit him because, you know, energy conservation. So VB is parallel to the tangent of the loop. Yes, that's always true. If the object always moves like a car will follow the path. So at the top of the loop, there is no normal force acting on the car. Yeah, okay. All right, so let's move on. So the next thing to talk about, I said I would talk about the potential energy function for the elastic force. So let's do that. So this would be the potential energy associated with a mass being attached to a spring, and that mass is stretched. So Honks Law, hopefully you guys remember this, I've brought it up myriad numbers of times now, is effectively that the force from a spring, or the elastic force due to a spring on a mass, is negative k times x minus x naught, where x is the position of the object that has the force on it, and x naught is the equilibrium position. So for a picture here, imagine that, say, your spring is here, your mass is here, and maybe its equilibrium position is located here. So x naught would be this vector, and x would be this vector, just as a quick picture. And so this x minus x naught business is a displacement vector from equilibrium. So for the sake of simplicity, let's say that x naught is equal to just x naught times I hat. It's just in the I direction or in the x direction, and that x is just x in the I direction. So I'm just consider this just be a one-dimensional problem. So the spring lies along the x-axis. Then we can calculate the work. The work done by a spring from A to B. Well, this is going to be equal to an integral from xa to xb of the force, which is negative k x minus x naught I hat dot I hat dx, or sorry, dx I hat. So here is our dl, and here is our force. So we can simplify this integral. This is then the integral from xa to xb of negative k x minus x naught dx. Yeah, so this picture is just describing what I mean by x and x naught. The x naught vector is just the vector that points from the origin to the point of equilibrium, and set similarly with x. All right, but now this is an integral that we can just do, right? We can just explicitly do this. It's just an integral that depends on x. And so we get negative 1/2 k xb minus x naught squared minus xa minus x naught squared. And so if we say that, let's let xb minus, or let's let x minus x naught equal x displacement, then this is just -1/2 k x displacement b squared minus x displacement a squared. So that is the displacement, that is the displacement distance when the block is at position B and respectively position A. And so that is -1/2 k delta x displacement squared. Notice that the squared is inside the delta because you want to square the displacement and then take the difference, not take the difference and then take the displacement and then square it. There's the order matters here. So and just for clarity, x displacement is just the magnitude of x minus, or sorry, the absolute value of x minus x naught. Or you could even think of it as the magnitude of the vector x minus x naught. Both are equivalent. So what does this imply? Well, this implies that the elastic potential energy is, well, it's the negative of the work done. So it's just 1/2 k delta x displacement squared. And so what does that tell us about what the potential energy function should be? Well, it tells us that PE elastic, again, at k can't change, so this should be as a function of x. This is 1/2 times k times x displacement squared plus u naught. Now, what I'm writing here, this whole x displacement, this secretly means x minus x naught. That's all. So we could have written that out. In fact, I think I probably will, just for clarity. This is 1/2 k x minus x naught squared plus u naught. Now, let's just break this down for a minute. So we can check that if you take x, I'll get to that in a minute. But yeah, you're right, it is some arbitrary constant. We can check that if you take the, difference, say if we do PE elastic, I'm just going to abbreviate PE sub E of XB and subtract it from PE sub E of XA, we would get 1/2 k XB minus x naught squared minus XA minus x naught squared. And the u naughts will cancel out. And the point is that this matches what we had up here, up to a minus sign, which is what we expect. This is delta PE elastic. So this is a good formula. And here u naught is just a constant because all we care about is the difference in potential energy between 2 points. And as long as the potential energy function is correct up to a constant, that constant will always cancel out when you take the difference, right? So when I subtract these two things, you get plus u naught and then minus plus u naught, and those just are going to cancel out and give you 0. So that's why we can add that. Now, by convention, we often set the potential energy elastic at x naught equal to 0. That's just a choice we make, where x naught here is the equilibrium point of the spring. It's elastic potential energy is the same as spring potential energy. It's just the name. And so what does this imply? This tells us that the potential energy elastic of x naught, well, that should be equal to, sorry, let me put this over here. 0 equals potential energy, the elastic potential energy at x naught, and so we can plug that in. What do we get? We get 1/2 k times 0 squared plus u naught, which tells us that u naught is 0. So the convention that we use typically is that the potential energy, the elastic potential energy as a function of x is just 1/2 k x minus x naught squared. That's the formula that we'll use most of the time. In a little bit, we'll actually see an example where we don't use that, but for the most part, that's what we're going to use. All right, so those are the two potential energy functions that we're going to see a lot, but we're not done yet, because remember that we were talking about three different types of energies. We had kinetic energy, which we've already discussed. We discussed it a while ago. We have potential energies, which we've now given two formulas for two different potential energies. We have yet to talk about thermal energies. So let's do that really quick. So the question is what is thermal energy? It's often abbreviated ETH. So it's generated when a non-conservative force like kinetic friction does work. So it is caused by work done by non-conservative force. Other examples would be drag. So let me give an example. So this example is kind of hard to draw, so I'll do my best. Let's say that we have a frictionless surface. Let's call this frictionless. We have a book that's rough on top up here. And we have another book. And by the way, we're neglecting gravity here. Well, no, I guess we can't neglect gravity. We're assuming that all of this is taking place very quickly. We have another book, say book A, that is being pushed onto the edge of the second book quickly. So the definition of elastic potential energy, it's just spring potential energy. It is the potential energy associated with the spring force, with the elastic force. All conservative forces have potential energies. Gravity is a conservative force, so it has a gravitational potential energy. Springs or the spring force, Honks Law, it is a conservative force, so it has an associated potential energy as well. So right now, it's just a function that describes that you're able to use to take, or that you're able to use to describe the work done by the spring force. That's all. Right. So imagine that this book A, they're like one is just hanging over the edge of the other, and that B is initially stationary and A is sliding. So what's going to happen is A will come into contact with B while it's moving. It will push B along, and B will slow down A, and eventually they will just be moving together, both of which are stopped, but they will move slightly slower. So the question is how can we analyze the work done there? So this is books before contact. This is kind of a contrived example, but I hope it'll get my point across. And then later on down the line, we have book B with its rough edge, and then we have book, let's line them up. And we have, and let's say that it stops perfectly on top of the other one, and book A. This is the books after contact. And by the way, they're still moving together, right? And now they're just held together by, yeah, this is an example of an inelastic collision. And we'll get to collisions next week. But yeah, this is a good example of that. So they're moving together and they're being held together by static friction here. So let's look at the distance that box B, or that book B traveled. It traveled, say, distance delta xb. And let's look at the distance that book A traveled. It traveled a distance delta xa. We're going to need those distances because we want to compute the work. So if the system we're computing, or if the system we're worried about is book A, well then the work done on it should be 0, or sorry, less than 0. One way to see this is by using the Work-Energy Theorem. The only external force is friction, which is pushing it in the opposite direction of its motion. And so, and alternatively, another way to view this is that the work must be negative because its kinetic energy decreases. And the original formula for the Work-Energy Theorem is this: work is equal to the change in kinetic energy. And so if the kinetic energy decreases, so does the work, or the work must also be negative. If the system is book B, i.e., if we're just interested in the motion of book B, then the work done on it is positive. And that's because, again, the kinetic energy of book B increases. Initially, it was at rest, and then it started to be in motion. So what if the system, and by the way, we could have just explicitly computed those works, but what if the system is book A and book B? Well, the work done on book A is equal to negative F times delta XA. F here being the frictional force between the two books. The work done on book B is, well, the force is the same, but the distance is different. This is F delta XB. Now let's talk for a minute about these signs. Yes, Matthew, the book A's work is less than 0 because it's slowing down. So these are just explicit values for what these for what the works would be here. Notice that this is positive. Delta XB is positive. Delta XA are both positive. And so the so these are just formulas for the why should there be an I hat? These are just formulas for the work done. And the friction forces in particular, these forces are the same on purpose because they are equal and opposite pairs, right? The frictional force from B on A is equal and opposite to the frictional force from A on B. So what is the work on both books? Well, it should be the sum total of the work on each. So this is F times delta XB minus F times delta XA, which is just negative F delta XA minus delta XB. Now, importantly here, this is the distance that book A slid across book B. In particular, that's the distance that that A was rubbing against B, right? That is that difference. And so the work done is just the, well, I can write it. The work done is just negative F times delta X, let's call it the rubbing distance, the distance that they were sliding or rubbing across each other. And that is, of course, negative, because this is F times negative F times delta. There we go. F is positive, the distance that that book A moved across book B is positive, so this whole thing is negative. So the point is that we can now we can see that Shawshank. So yes, the system as a whole is slowed down, but more so even than it would have been if they were just attached initially, right? Yeah, the whole system is slowed down. So hold on, let me get to this in a minute. So because there's no external friction, i.e. the surface that it's sliding on is frictionless, we can write down the Work-Energy Theorem relatively easily. There's no external friction. That's important when we're talking about the system being just the two books. The Work-Energy Theorem is 0, which is because there's no external forces. We're going to ignore gravity here because gravity is only perpendicular to the motion, so it won't contribute anything to work. So we have 0 equals the change in kinetic energy of the system plus the change in thermal energy of the system, i.e. this is equal to the change in kinetic energy minus the work done by both, or the work done on both books. So what does that say? It says that the change in kinetic energy of the system is equal to the work done of both books. And we know that that's negative. So that tells us that the kinetic energy, the final kinetic energy, is less than the initial kinetic energy of the whole system. So you might ask, where did that energy go? Right? We've talked a lot about energy conservation, and typically, you guys have even heard as lay people that like energy is neither created nor destroyed or something like that. Well, of course it's not. Where it went is that it increased the temperature of the books. And maybe it made some sound too. That's another form of dissipative energy or thermal energy. So the whole point is that the non-thermal energies of the system decrease when some of it is transformed into thermal energy. and now there's just less energy available and you can't get that back. So you might ask, why can't we get E thermal back? So, I mean, that's a hard question to answer. I'll give you some bullet points and I'll give you some thoughts that you can maybe look up or you can check it out in the textbook. Would you get mathematical calculation questions about lost energy in this class, or does that come later? No, that'll certainly, you mean today? I mean, it'll certainly happen in this course. And we kind of got to it today. This was a calculation about lost energy. Anyway, hopefully that answers. So one reason or one possible explanation for why we can't get that thermal energy back is that molecular motions are random. So whereas standard kinetic energy is the kinetic energy that we calculate in this course is orderly. It's every single molecule in the object moves at the same rate on average. Thermal energy, which is effectively kinetic energy of molecules, that's more randomly distributed. So you can go from an orderly arrangement of kinetic energy to a disorderly arrangement just by shuffling things up. But it's very, very hard to go from a random arrangement, molecules moving every which way, to every molecule moving in the same direction. For a better or more thorough discussion of this whole microscopic versus macroscopic models of energy, what I would suggest you do is look at section 3.5 in the Libre text. There's a whole discussion there on this business of macroscopic versus microscopic energy models. Right, so yes, I can explain why they're both negative, or why it's negative. So hopefully you agree that the work done on book A is negative. The work done on book B is positive. One way to see that is the work done on book A relates to the change in kinetic energy and so on. And we can actually calculate this explicitly. This is equal to let's call it XA initial and XA final. And the force is in the negative X direction. That's the frictional force. So we have negative F I hat dot into dx I hat. And so we can just do this integral and we get that it's negative delta XA. Whereas for the force on book B, the force is in the right going direction. And so the force there is positive. And so what you get is when you find the total work done, you just add the two up. And we find that they're the same, except they have different values for these lengths that they've traveled. Book A traveled further, so the negative work done is more because the work involves both the magnitude of the force and the distance traveled. And so because it traveled further, it has more negative work than book B has positive work. And so when you add them together, you get something negative. Hopefully that's straightforward enough. All right, so far we've talked a lot about this potential energy function. What we haven't done is explained, besides work, why we actually care about it. So let's do that. Let's talk about force and how it relates to the potential energy function. And by the way, there's not just one potential energy function, right? Like for any given conservative force, there is a potential energy function. The whole point, though, of this whole thing is that when conservative forces are involved, we don't really need to compute work directly to apply the work-energy theorem. All we need to do is just know what the potential energy function is, and then we can just plug that in and get what the work is. Instead of having to do any sort of integral, we can just write that 0 equals delta KE plus delta PE. Instead of writing, 0 equals delta KE minus work conservative internal, right? Like, and maybe we even put external work over here. And that's certainly easier because if you already know the formula, then you're just subtracting two numbers in this formula rather than doing a full integral here. So certainly it is useful. And so there must be some sort of relationship between a force, which you use to obtain the work, and a potential energy function, which is literally just two numbers subtracted from each other. So the question is what is that relationship? What is the relationship between force and its potential energy? So what we're going to do is we're going to consider a small amount of work. And when I say small, I mean like infinitesimal. And we're going to call that dW, d being the infinitesimal standard notation, done on an object. An object by force, call it F. So how would we compute that? Well, we know that the work done, the total work done over a full path is the integral of F dot dl. And so what you're doing is you're basically just adding up the amount of force at each point along the path, and you're just adding them all up. So if we just have a tiny amount of work done, what that means is that you're just looking at the force over a very tiny distance. So dW then, we could quite easily, and I hope this isn't so surprising to you, that this is just the force times a small chunk of path, right? You guys know this whole business about derivatives and d's kind of canceling out integrals. That's basically all we're doing here. So we can now just write this out explicitly. The force is Fx in the I hat direction plus Fy in the j hat direction plus Fz in the k hat direction. And that's dotted into the path. And the path is dx in the I hat direction plus dy in the j hat direction plus dz in the k hat direction, right? It could be in any which direction. And this will tell us a displacement in all directions. If we have a force in that direction, then we might have a displacement in that direction. So this is just the sum Fx dx plus Fy dy plus Fz dz. Now what this means is this term tells you if there is a displacement in the x direction of length dx, then that term contributes f sub x times that displacement distance. This term says the same for y, this term says the same for z. Now importantly, if there's no displacement in say the y and z directions, those terms wouldn't be there. So hopefully there's nothing surprising going on here. All I've done is taken a dot product and manipulated symbols. So if this is the only force on our system, if F equals F net is what I'm saying, then there are no other external works, right? Or sorry, there are no other works that can be done. So the work-energy theorem tells us that dW equals dKE. What do I mean by that? I just mean a small change in the kinetic energy. That work will be associated with the speed very slightly increasing or decreasing or whatever. If the force is conservative, then a small change in the kinetic energy leads to a small change in the potential energy of opposite sign. It's balanced by a small change in PE. All I'm doing now is I'm saying, look, if F is conservative, then we just call whatever the source of that conservative force is, we call that part of our system. And now we're left with 0 equals dKE minus dW. But if F is conservative, then we can write dW as plus dPE. That's the takeaway here. So if F is conservative, we get this just by making our system larger. So that implies, well, I mean, an implication from this, or one of the reasons I used, is that dW is negative dPE, and that should not be surprising at all, right? The work done is, the potential energy, a small change in the potential energy is the negative of a small amount of work done. That's just the definition if the force is conservative. So now let's just work with an explicit example. So, and by explicit example, I mean still symbolic, but more explicit. Now suppose that F, it's just a vector in the x, or it's just a force in the x direction. So what does that mean? Then we have that the work done looking up here, the work done, dW, is equal to f of x, or f sub x dx, right? Because fy and fz are both 0. And that, but dW is negative of the change in potential energy. So what do we have? We have f sub x dx equals negative change in potential energy. Small change in potential energy. The reason I'm doing all of this small, by the way, is because of what's about to happen. I'm going to pull a thing that they tell you not to do in math class. I'm going to divide by dx. So then f sub x is just negative dpe dx, and that's a derivative, right? That is, if you have the potential energy function and you take the derivative of it with respect to x, you get the force in the x direction. So from now on, just as a notation thing, from now on, we use the letter u, and we'll write like u of x, or u of xy, and so on, for PE from now on. So you'll see me write things like u sub g, or u sub elastic, and so on. Yeah, I can, and I'm actually going to spend some time on the math here, just because I know it's going to be tricky. So, so what I did is I just took the work up here, up top, and in particular, I looked at this. I looked at what happens to all of this calculation that I just did when the force only points in the x direction, right? If the force only points in the x direction and it's conservative, and our system includes the source of that force, then we get this expression that comes directly from what we did up here. We get that expression, and then from the fact that that dW is the negative of the small change in potential energy, we can follow this equality down, and then all I did was divide by dx. I took the dx that was present on the that was there because the objects traveled a small amount of distance in the x direction, and I just divided the change in the potential energy by that small distance. And that is what a derivative is. It's just a limiting process of dividing a small change in a value of a function, in this case the potential energy function, by a small distance traveled. So before we move on, it didn't. Oh, you're talking about perhaps here. So that's just the work-energy theorem, right? A small amount of work done is equal to the change in the potential energy, or sorry, change in the kinetic energy. And then all I said was, look, if the force is conservative, then that small amount of work done can be explained by a small change in potential energy with the opposite sign. So that's where we get this equation. Maybe I shouldn't have boxed this. Maybe I should box this. This is the important part. Right. Okay, so now I have to take a break and introduce something called partial derivatives. I'm only going to talk about these briefly because there's nothing spooky about them. So a partial derivative, some of you may have seen this in math so far, but I think most of you won't have. Partial derivative is often written, or a regular derivative might be written df dx, right? A partial derivative, and the implicit thing here is that f is a function of x, right? That's important. But let's say we wanted to do a derivative. Let's say a function was a function of x and y, but you only wanted to see how it changed in the x direction. What would that amount to? How does f of x and y change in the x direction? Well, what that would amount to is just imagine that you're treating the y variable as just a fixed thing. You don't take the derivative with respect to it because you're just imagining, you only care about how the function changes when x changes. So just imagine that y is fixed. So then you could write the derivative with respect to x. You would write this. This is the notation that we use. So these curly d's, they're kind of like backward sixes. That means partial derivative. And when I say partial derivative, all it means is you take the derivative with respect to a single variable and hold all of the other variables fixed. So what this means is this means the limit as h goes to 0, you guys have all seen a definition like this, of f of x plus h and y minus f of x and y divided by h. So all I'm doing is I'm just treating the y as if it weren't there and then taking the derivative with respect to x. So for example, let's say f of x and y is x squared plus y squared. Well, then we can take the partial derivative with respect to x. It's implied here that it's a function of x and y. And that's just, well, you know how to take derivatives of things that are added. That's just 2x. Because this y is treated like a constant, and derivatives of constants are 0. Similarly, the partial derivative of f with respect to y is just 2y, because x is treated like a constant in that case. We can look at something more complicated. Let's say we have f of x, y equals, say it's x squared times y. Well then, df dx, well, again, you treat the y as a constant and then just take the derivative as you normally would. This would be 2 times x times y, right? You treat the y as if it's just kind of attached and along for the ride. Similarly, df dy would be x squared. Because x squared, if x is a constant, then so is x squared, and then it's just a number times y, and the derivative of that is just that number. So the whole point here, and by the way, partial derivatives like this will be in general will be functions of all of the variables. Partial derivatives are just a useful way of handling three-dimensional things, or being able to use calculus on three-dimensional things. So it's not right. It's not that the y is 0, it's that the derivative of y with respect to x is 0, because y is constant when you're changing x. Think of it like, yeah, so I'll leave it at that. And there's a whole bunch of resources on partial derivatives, both in the LibreText, but also if you just Google partial derivative tutorial on YouTube, you'll get a whole bunch of sources. So basically just think of them as you treat everything else as if it's just like, let me give another example. Let's say we just had f of x, and that function was just like a times x plus b, right? Where a and b are just some constants. Then the derivative of f with respect to x, sorry, I'm used to doing the partial derivative symbol, is just a, right? You guys all know that. So all you're doing when you take a partial derivative is you just treat everything that's not the variable you're interested in, like this y squared here, you just treat it as if it were just a constant. That's all. And then you just take a derivative as normal. Hopefully that clears things up. But all it is it's a way of just generalizing this idea of a derivative to more than one dimension. So hopefully you can see from this understanding here that not only is the force in the x direction the negative derivative with respect to x, in fact, it's true that the force in the x direction for any potential energy function is the negative partial derivative of the potential energy function with respect to x. The reason there wasn't a partial derivative here was because it was only a function of x. But once it becomes a function of more than just x, it has to be a partial derivative. Similarly, the force in the y direction is the negative partial derivative with respect to y, and the force in the z direction is the negative partial derivative of u with respect to z. So where does that get us? That gets us that the force, if you are given some potential energy function, the force is negative du, or partial u partial x, in the I hat direction, minus partial u partial y in the j hat direction, minus partial u partial z in the k hat direction. And so if you're given the potential energy function, you can get the force back. And that's the part that makes potential energy functions so useful. I mean, it's great that you can use them to compute work, but it's even better that you can describe an entire force, an entire conservative force, just by a single function without having to know all three components, because you can get back the force from the potential energy function just by taking a few derivatives. So there's a notation here that we'd write the force is the negative gradient of U, where this symbol, which looks like a vector, it's not actually a vector. This is I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. And this thing is called the gradient. And so you can just think, if you just put a u here, then those derivatives act through. And so you would have three, like you distribute the derivatives onto u, and you would get what we have up here. Right, so just a quick note, this only works for conservative functions, right? So let me write a sentence, and then we'll probably call it there. This is another definition of conservative forces. A force is conservative if and only if it can be expressed. I know that this is formal language, but it's useful, as the negative gradient of a potential energy function. So we did not get through a lot today. That's really a bummer. Right, so the whole point here is that if you have a force, then you should be able to express, if that force is truly conservative, you should be able to find a potential energy function for which that force is the negative gradient. And I'll go into more detail on examples that we know next time, but we are now out of time. I'm not going to say for certain that we will go over over on Friday, but we might, because we do have a lot more to cover, which is unfortunate. So Shreyas, so yes, so you can prove that force is conservative by proving its curl is 0. That is true. We're not going to do that, just because it's a mess, and you guys haven't seen the definition of the curl yet. So it was even hard to convince the department to let us talk about gradients when you haven't taken 21C, I think. All right, so that's all I have for you guys today. I'm going to stop the